The drone launches from the floor of the Vilcanota Valley in the shadow of the Andean cloud forest, carrying a unit about the size of a shoebox attached to its undercarriage. The unit is a LiDAR scanner, light detection and ranging, and it fires laser pulses toward the ground at a rate of hundreds of thousands per second, recording the return time of each pulse to build an extraordinarily precise three-dimensional model of whatever the laser light touches on its way back up. Through clear air to bare ground, this produces a topographic map of extraordinary resolution. Through cloud forest, through a canopy layer, a mid-canopy layer, an understory, and a ground-level jungle mat that collectively reduce visibility to a few meters, this produces something that was essentially impossible to obtain from any position on or above the ground until multi-return LiDAR sensors were developed with sufficient pulse density and processing sophistication to extract ground returns from beneath the vegetation. The pilot watches the drone rise above the canopy and begin its systematic survey pattern. The operator monitors the data feed, and somewhere in the real-time point cloud appearing on the processing screen, the outlines of things that have not been seen by any human being in 500 or 600 years begin to emerge from the filtered ground returns. This specific operation, led by Dominika Sieczkowska from the University of Warsaw's Center for Andean Studies, produced one of the most significant recent archaeological discoveries in the Machu Picchu region. The revelation that a ceremonial complex known as Cachabamba, located approximately 5 miles from the main Machu Picchu citadel and believed to be a reasonably well-documented site, had approximately 12 undocumented structures sitting within 60 feet of its main ceremonial area. They were so close, and we didn't even know they were there, Sieczkowska said. 60 feet. The distance from one end of a modest house to the other. 18 meters that separated the known from the unknown for the entire century since Hiram Bingham introduced Machu Picchu to the outside world in 1911. Not 18 kilometers in a remote jungle. 18 meters from structures that archaeologists had visited, studied, and written about. Hidden by vegetation so dense, in a climate so relentlessly productive of plant growth, that surface-level survey was physically incapable of revealing what was immediately adjacent to what was already known. This is the discovery situation at Machu Picchu in the 20 Quinostes, a site that has been intensively studied for over a century, that has been mapped, measured, photographed, and described in thousands of scientific papers and popular books, that receives 1.5 million visitors annually and is one of the most recognized places on Earth, and that is still, demonstrably and repeatably, yielding discoveries of fundamental significance when new instruments are pointed at it. Not from distant orbits, from drone altitude, within walking distance of the tourist entrance. And beneath the surface, where no drone can see, but where other instruments have been producing an equally surprising picture, the story is the same. The most consequential engineering at Machu Picchu is the engineering nobody can see, and it has taken the last 3 decades of systematic investigation to characterize it with any precision. What the scientists have found, above the surface in the jungle and below it in the engineered fill layers that the Incas designed and built before a single visible wall was raised, represents a site whose actual scope and sophistication exceed what any century of surface-level archaeology was capable of detecting. The technology story begins before LiDAR. It begins in 1994 with a different kind of instrument, an excavation. Civil engineer Kenneth Wright arrived at Machu Picchu with a research permit, a Peruvian archaeological collaborator named Alfredo Valencia Zagara, and a specific question about what lay beneath the main plaza. His professional background in water management systems had led him to suspect that the visible hydraulic sophistication of the site, 16 ceremonial fountains, a 749-meter aqueduct from a spring-fed source, carved stone water channels threading through the entire urban sector, was the visible expression of an engineering tradition that would have applied the same systematic intelligence to the invisible parts of the problem. He was correct in ways that exceeded his initial expectations. Digging 9 feet below the surface revealed a sophisticated underground world that most visitors never see. 3 feet of rich topsoil carefully curated for optimal drainage, sandy, gravelly substrata engineered for water filtration, a white granite drainage system made from waste rock recycled during construction, and 130 or more strategic drainage outlets built into the original wall construction. The most counterintuitive element of this finding was the white granite. This rock turned out to be white because it was white granite originally, before turning color with age. So while we look at Machu Picchu today and see gray buildings, when it was built, it was white granite. At any rate, the white granite told us a lot about their engineering ingenuity and their desire to provide good drainage for Machu Picchu, because without good drainage, there would be no Machu Picchu existing today. The white granite chips, the waste material from shaping and fitting the wall blocks above, had been collected and used as the permeable matrix at the base of the engineered fill layer. This is resource management of a specific kind. recognizing that the byproduct of one phase of the construction has properties that make it the ideal material for a different phase of the construction, and designing both phases to take advantage of this. The chips were porous, they were angular, with irregular surfaces that prevented tight packing. They were granite, durable, and chemically inert, immune to the decomposition that would have degraded organic drainage material over 5 centuries. They were, as drainage aggregate, nearly ideal, and they were free, produced in quantity by the construction of the walls that rested on top of them. At the very bottom of the excavation was a golden bracelet, the only gold found at Machu Picchu, and we are very pleased to have that. It's in the Cusco Regional History Museum today. The bracelet was a ritual deposit placed at the level of the foundation before any fill or drainage material was laid. Its placement at the lowest accessible point of the construction, the deepest level that would be sealed permanently beneath the engineered fill, represents the Inca practice of paying respect to the Yuku Pacha, the inner world, the world below the surface that Inca cosmology understood as the source of life and fertility. The invisible engineering was not just functional infrastructure, it was sacred space. At Machu Picchu, engineers estimate that 50 to 60% of the total construction effort went into underground work, including foundations, drainage, and site preparation. This proportion, consistently arrived at across multiple engineering analyses since Wright's initial excavation, means that the Incas invested more labor hours in what cannot be seen than in what can. The terraces, walls, temples, and plazas that draw 1.5 million visitors annually represent the smaller half of the construction effort. The drainage matrix, the foundation engineering, the site grading, the underground channel network, these represent the larger half, and they are the reason the visible half still exists. The 2023 scientific report study by Massini, Romano, Sieczkowska, and colleagues extended Wright's single excavation into a comprehensive geophysical survey of the entire main citadel area. 5 complementary survey methods were used to investigate the subsoil at different depths: multispectral imaging from satellite and UAV, electrical resistivity tomography to characterize the electrical behavior of the subsoil up to 10 meters, ground-penetrating radar to detect objects and bodies up to an expected depth of 2 meters, and magnetic surveys in a gradiometric mode to detect variations of the Earth's magnetic field, referable to any anthropization processes. The combination of methods was specifically designed to address the limitations of each individual technique. GPR provides high spatial resolution, but limited depth penetration, and its performance varies significantly with the electrical properties of the material. ERT provides deeper penetration, but lower spatial resolution. Magnetic surveys detect materials with different magnetic susceptibility than the surrounding soil, particularly useful for identifying fired structures, like hearths and kilns, and some types of stone construction. Satellite and UAV multispectral imaging identifies surface and near-surface features through spectral, anomalies associated with buried structures, differences in soil chemistry, moisture content, and vegetation density that often appear above buried archaeological features and are detectable in the reflectance patterns of vegetation and soil. Results from ERT and ground-penetrating radar located the bedrock at a depth from 2.0 to 3.5 meters below the current ground level and virtually reconstructed the drainage basin. The bedrock surface model, the topography of the ridge before any Inca construction began, shows a more rugged, less organized surface than the finished site. The Incas did not simply build on a convenient ridge. They engineered the ridge, grading high points, filling low points, creating the level plazas and uniformly sloped terraces that the finished site displays. The fill volumes implied by the difference between the natural and engineered topography are substantial. Tens of thousands of cubic meters of material moved, graded, and placed in specific sequences to produce the drainage and structural properties required. The geological context that the geophysical surveys confirmed adds another layer to the understanding of why this specific ridge was chosen. 2 principal faults, the Huayna Picchu Fault and the Machu Picchu Fault, formed a wedge-shaped structural block on which the ancient Inca people built their city. The Machu Picchu Fault influenced the location at which the Machu Picchu spring emerges, the same fault system that provided the geological conditions for the primary water supply also provided the building material. The inherent rectangular joint pattern that the Inca workmen recognized and masterfully used as building stones to construct Machu Picchu. The site was not selected for its scenic qualities, though those are undeniable. It was selected because the geology, the specific combination of fault system, joint pattern, and spring emergence, provided all the preconditions that a permanent, hydraulically sophisticated royal estate required. Now, the LiDAR discoveries, which represent the most recent and, in some ways, most dramatic chapter of what modern technology is revealing about the full extent of the Machu Picchu complex. Earlier airborne LiDAR attempts at Machu Picchu in 2016 by the Peru LiDAR project produced disappointing results due to dense understory vegetation. The 2024-2025 discoveries succeeded because of improved sensor technology, modern multi-return LiDAR systems with higher penetration capability, optimized flight, parameters at lower altitude, slower speeds, and increased overlap, and advanced processing algorithms with better vegetation filtering and ground detection. The technical distinction between single-return and multi-return LiDAR is the key to understanding why 2016 failed and 2024-2025 succeeded. A laser pulse fired into a forest canopy encounters multiple surfaces as it penetrates downward: the top of the canopy, the upper branches, the lower branches, the understory layer, and finally the ground. A single return system records only the first surface encountered, typically the canopy top, and provides no information about anything below. A multi-return system records the timing of reflections at each surface, including the ground reflection that arrives last and weakest, after the pulse has been attenuated by all the surfaces above. Processing the ground returns from multi-return data, using algorithms that distinguish ground returns from vegetation returns based on their spatial statistics, produces a digital terrain model of the ground surface beneath the canopy. The quality of this ground model depends on how many ground returns reach the sensor, which depends on the pulse density, the flight altitude, the canopy density, and the processing algorithm. The 2024-2025 surveys improved all of these parameters simultaneously: higher density sensors, lower flight altitude, more passes over each area, and better vegetation filtering algorithms. The result was a ground model with sufficient resolution to identify stone walls, paved surfaces, terrace edges, and channel features beneath vegetation that blocks all other forms of remote sensing. Peru's Ministry of Culture announced the findings following preliminary archaeological reconnaissance carried out in July 2023 around the Mandor Wall, close to the Inca citadel of Machu Picchu. Among the most significant discoveries is the 1.2-kilometer road, whose layout displays characteristics associated with Inca construction techniques. Researchers have also investigated a distinctive zigzagging pattern along its route, suggesting that the road may have been built during the Inca Empire. The zigzag is one of the most reliable diagnostic features of Inca road construction in steep mountain terrain. On slopes too steep for direct descent with loaded carriers or pack llamas, Inca road builders employed a specific switchback design, a series of traverses across the slope face, each reversing direction at an angle that maintained a manageable gradient while gaining elevation. The specific geometry of the reversal points and the construction, details of the traverses, paved surfaces, retaining walls at the outer edges, drainage channels along the inner edges, are sufficiently distinctive that a well-preserved example can be confidently identified as Inca without excavation confirmation. The 1.2-kilometer road is the single largest individual discovery, but the total road network revealed in the survey extends to more than 2.5 kilometers of previously undocumented road infrastructure, along with the 12 structures at Cochabamba, the underground water channels serving those structures, and additional features that are still being processed from the survey data. LiDAR analysis has revealed that Machu Picchu was not an isolated mountaintop retreat, but the hub of a geographically vast complex extending far beyond the visible stone structures tourists see today. The implications of this for the historical understanding of Machu Picchu are significant. The site has been interpreted since its rediscovery as a royal estate, a retreat for the Inca Emperor Pachacuti, built in the 15th century and used by his royal lineage, his Panaka, after his death as a place of memory and ceremony. This interpretation is well supported by the documentary evidence and by the archaeological record. But a royal estate of the Inca imperial period was not a small private residence. It was an administrative and ceremonial complex that included staff housing, agricultural operations, producing food for the estate and for tribute, ceremonial facilities for the rituals that maintained the connection between the living and the dead emperor, and road connections to the broader imperial network. The Cochabamba complex, now revealed to be larger than previously documented, is consistent with its role as a ritual entry point for pilgrims approaching Machu Picchu along the Inca Trail, a place where travelers were ritually purified through ceremonial bathing before entering the sacred space of the main citadel. The 12 previously unknown structures surrounding the known ceremonial area could represent staff housing, storage facilities, or additional ceremonial spaces associated with this purification function. The underground water channels that supplied the ritual baths are engineering at the same level of sophistication visible in the main citadel, the same knowledge of hydraulic design, the same systematic approach to water supply and distribution applied at a satellite site miles from the main complex. The road network connecting these components is the physical expression of the administrative organization that made the estate function. Roads moved food from the agricultural terraces to the storage facilities. Roads moved personnel between the main citadel and the satellite complexes. Roads moved goods in and tribute out, the 1.2-kilometer road in the Mandor area was not a casual path. It was infrastructure. Planned, constructed to Inca engineering standards, integrated into the movement network that made the estate's operations logistically viable. What technology has revealed about Machu Picchu in the 3 decades since Ken Wright first excavated the white granite chips from 9 feet below the main plaza is a site whose actual character and extent were significantly underestimated by a century of surface-level investigation. The surface-level investigation was not inadequate by the standards of what surface-level investigation can achieve. It was limited by the fundamental epistemic constraint that every tool has. It can see what it can see and not what it cannot. Surface survey cannot see through 9 feet of engineered fill to the drainage matrix below. Surface survey cannot see through 60 feet of cloud forest to the stone walls beside the known ceremonial complex. Surface survey cannot reconstruct the topography of a ridge before the Incas began reshaping it with engineered fill. The instruments that can see these things, GPR, ERT, LiDAR, are not new in principle. What is new is their precision, their deployment platforms, drones rather than aircraft, their processing algorithms, developed over decades of accumulating archaeological applications, and the systematic application of multiple complementary methods to the same site simultaneously. The 2023 scientific report study applied 5 methods simultaneously. The 2024-2025 LiDAR surveys used multi-return systems optimized for cloud forest penetration. The combination is producing, for the first time, a picture of Machu Picchu that is not limited by what can be seen from the surface. And what can be seen from above the surface, once the vegetation is stripped away digitally, is a site that extends further than any map made from ground-level observation could capture. A hidden world beneath Machu Picchu revealed by laser technology. Not beneath in the literal underground sense, though that world exists too and has its own extraordinary discoveries. Beneath the vegetation, beneath the cloud forest that has been growing over structures that were abandoned 5 centuries ago and immediately reclaimed by a jungle whose growth rate makes it one of the most efficient archaeological concealment systems on Earth. Every season of new survey reveals more. The road network is still being traced. The structures around Chalchabamba are being mapped and characterized. The geophysical surveys of the main citadel are being refined with additional data points. And in January 2025, the ground-penetrating radar survey under Cusco confirmed the existence of the legendary tunnel system connecting the Temple of the Sun to the fortress of Sacsayhuaman, the Chincana described in colonial chronicles as a labyrinthine underground passage, adding another dimension to the picture of Inca underground construction that began with Ken Wright's excavation at Machu Picchu 30 years ago. The Incas built for eternity, above the ground and below it, in the jungle and on the ridge, in stone and in water. The technology to read what they built has been developing for 3 decades. The reading is not yet complete. But what has been read so far, the underground world that makes the visible world possible and the surrounding jungle world that the LiDAR is only now beginning to reveal, changes the site from what the tourists photographed to something far larger, far older in its full extent, and far more sophisticated in its engineering than any century of looking at the surface could have shown. Subscribe, because the drones are still flying and the instruments are still pointing downward, and what they are finding continues to exceed what anyone expected to find.